Hello there. So, in this video, I want to talk a little bit about Euler's formula. And specifically, I want to explore it intuitively. If you don't know what Euler's formula is, let me go ahead and write this out. It says that I can express a complex number in the following way. R e to the I phi equals R cosine phi plus I sine phi. So, I want to go ahead and kind of explore this in a very intuitive way. I'm not going to be Taylor expanding e to the I phi out and then finding that it has the same Taylor expansion as cosine phi plus I sine phi. While that is a very rigorous and perfectly reasonable way to prove Euler's formula, it doesn't necessarily grant much physical intuition. And so I hope to kind of illuminates that e to the I phi immediately connects to circles and circular motion. So let's go ahead and think about this. Okay, so let's go ahead and start just by talking a little bit about the complex plane. We're going to go straight from the ground up. So if I have a complex number z, and this is defined as, I'm just going to say a plus bi, right, for some arbitrary a and b. We know that we can go ahead and break down z into two components. First, we have the real component of z, and this is simply equal to a, right? Because it's the real part. The imaginary part of z is equal to b. Notice how I'm not saying bi, right? The imaginary part of z is the component in the kind of imaginary direction. What do I mean by this? Well, I can go ahead and graphically represent z in the complex plane. I'm going to define my x-axis. My x-axis is defined as the real part of z, and my y-axis is defined as the imaginary component of z, right? And of course, with this definition of the real and the imaginary component, it becomes a really trivial exercise to go ahead and represent this imaginary number graphically, right? I can simply go out some distance a in the x direction, and then I go some distance b in the y direction, and there we go. This is a graphical representation of a plus bi, where I went ahead and I graphed a and b, or the real component and the imaginary component of my complex number on the complex plane. Hopefully that makes perfect sense. Let's go ahead and think about another way that we can go and represent this complex number. I can go through and define a radius out from my origin, correct? This radius is going to have some radius r. I can also go through and define an angle phi that this radius is going to form with the xy axes, or specifically with the x-axis, right? Let's go ahead and break down this triangle into its components. I'm going to go ahead and draw this x direction component just under the x-axis so that we can see it. Although we know that this component is actually on the x-axis. All right, great. Well, if I'm given some radius r and some angle phi, could you tell me what this component on the x-axis is? Well, of course, this is r cosine phi. And of course, on the y-axis, this is r sine phi. So, what's our total complex number? z, and I'm going to put just a little note that this is in polar coordinates, whereas before, to contrast this with the fact that up here we were just using rectangular coordinates, right, or Cartesian coordinates. So z with my polar coordinates is equal to r cosine phi plus, don't forget to multiply this vertical component by I. We have I times r sine phi. Very good. And so from here I can go ahead and take out the r and write out cosine phi plus I sine phi, and this is equal to my complex number z. Okay, so we have the right side of this equation, right? And great, we know what this right side means. It means if I take a complex number z, I can go ahead and represent it in polar coordinates with some angle phi and some radius r, and then I can immediately write out the complex number where this r times cosine phi is going to spit out the horizontal component or my real component, and r times sine phi is going to spit out my vertical component on the complex plane or my imaginary component. Okay, so that was kind of a good warm-up, a little bit of a refresher on the fact that, yep, we can represent a complex number in polar coordinates. Now, what's not a trivial claim is to claim that this representation of polar coordinates can be compactified, right, in this really nice form here with a complex exponential, right? That this complex exponential here on the left is identical to the complex representation where we wrote out this as r cosine phi plus r times I sine phi, right? That's not a trivial fact, but hopefully I can bring this to light. So, if I have a complex plane, we're going to go ahead and use this complex plane to actually explore a dynamics problem. We're going to explore circular motion. So, I'm going to go ahead and draw in a circle. Oh, and first, of course, let me label our axes. There we go. And what's this circle? This circle represents the trajectory a particle is taking. It's moving through space, right? And this circle is going to have some fixed radius r, right? So if my particle is traversing this circle, right, and I'll go ahead and put this point down. This is my particle at some arbitrary point at time. At some arbitrary point in time, right? At this point, it's going to form some angle phi, right? And let's go ahead and note now that phi, of course, is a function of time, right? Because, of course, my particle is moving across the circle. Its radius isn't changing, but its angle with the x-axis here is absolutely changing, right? As it moves around. Awesome. All right, so before I keep going, let me just go ahead and call this the x direction. Let me call this the y direction. So I can go ahead and refer to the particle's position in terms of x and y as well, right? Instead of saying the real direction and the imaginary direction. So I need to put some constraints on this circular motion before we go any further, right? The first constraint I'm going to put on is I'm going to tell us where the particle starts. I'm going to force the particle. I'm going to constrain this problem. And let me go ahead and change this arbitrary position. I'm going to change this arbitrary condition to this light blue here. And this black, this is the starting position of my particle. So my particle is going to start on the x-axis. Okay? How can we mathematically describe this initial condition? Well, phi, my angle phi, at t equals 0, of course this is just equal to 0, right? We feeling good about that? All I've done is I've said, yep, this particle is traveling on this circular loop, and now we've defined at t equals 0, it starts here. Great. But also, this particle can move around this circle in any number of ways. It could be accelerating up here and then slow down, and then accelerate here and then slow down, and then accelerate. No. Let's lock this in. This particle is forced to move in uniform circular motion. So that means that d phi dt, my angular velocity, is always going to be equal to a constant omega. It has a uniform angular velocity, okay? And so we could also say that my angular velocity as a function of time is equal to, or sorry, not my angular velocity, sorry. My angle as a function of time is equal to omega times t. Hopefully that's absolutely clear. Let's go ahead and see now that we have these pieces of information. Can we propose an equation to describe the position of my particle at every location in time? Well, I'm going to go ahead and claim that my position as a function of time. Now look at this. Notice how we don't have to distinguish between an x position and a y position because the complex number encodes both of those things. It's so cool. So my z as a function of time is equal to capital R, which is a constant, times cosine phi. And what's phi? Oh, phi is just omega t, plus I times sine phi, or sine omega t. Beautiful. Let's go ahead and verify that this satisfies our initial condition here, that phi at t equals 0 equals 0. If I go ahead and I plug in 0 for both of these t's here, then omega t goes to 0 as well, just multiplication by 0. Okay, cosine 0, oh, that just equals 1. And sine 0 equals 0, so we have r times 1, and that's going to spit out r. Great. So, in other words, at t equals 0, yes, I am in fact at r in the x direction. And that's it. Beautiful. So this equation here perfectly describes the motion of my particle, which is rotating or going around in a circle with some constant angular velocity omega. Let's go ahead and describe my time derivative. If you're not used to the dot notation, I'll just go ahead and write this out as dz dt. So this was my position. Now I want to describe the velocity of my particle as a function of time. So this is simply going to be equal to, take the derivative, right? So this would be this is going to be r omega times minus sine omega t plus I times cosine omega t. While we're at it, let's go ahead and get an equation for the acceleration of my particle. This is just going to be r omega squared times minus cosine omega t minus I sine omega t. And if we go ahead and we pull out this minus sign, right, we have minus r omega squared times cosine omega t plus I sine omega t. I want us to make this connection, right, that if I group these terms together and I recognize that these terms here are identical to these terms in d squared z dt squared, right, then I can just simply rewrite this as minus omega squared z. I simply plugged in the position of my particle into this equation here. And so you can go ahead and more rigorously prove what I'm about to say here next, but I just want to point out that this velocity here encodes the obvious kind of direction of what you would expect the velocity of this particle to be, right? So let's go ahead and I'm going to call this statement 1, and I'm going to go ahead and call this statement statement 2. And from statement 1, immediately following statement 1, we can conclude, just with a little bit of math, we can immediately, though, conclude that the direction of my velocity is always going to be tangent, to this circular path here. That's a really powerful claim, right? But we can show it, right? I don't want to spend a bunch of time drawing out more triangles and messing this diagram up, but we can show that if my position is represented with r times cosine omega t plus I sine omega t, we have some other scalars here. If we swap this to minus sine omega t and I cosine omega t, that's going to result in us getting this tangent direction for our velocity. Statement 2 is much easier to see directly since we've rewritten it as minus omega squared z. Statement 2 tells us that the acceleration on our particle, right, if I'm at some position z, then, okay, what direction must the acceleration point in? Oh, okay, my acceleration needs to point inward, right? My acceleration needs to point this way. So this is d squared z over dt squared, right? So I have a lot of things now. I have my position is at some particle, or sorry, said that backwards. My particle is at some position in space z. My velocity of this particle is always going to point tangent to the circle that it's traversing, and its acceleration is always going to pull inward. Hopefully we're familiar with these ideas, and hopefully we've seen circular motion before, so this isn't that out there, right? But it should make sense, right? That if I have a tangent velocity and it's just acting this way, let's say I hid this acceleration pulling it inward. Well, then my particle would just keep moving out, right? It would just move in a straight line. But because I've added this additional acceleration pulling my particle inwards, right, is causing the particle to bend, right, instead of just moving outwards. And that's what's actually pulling it in and allowing it to move in this circle. But before I go any further, I just want to say one more thing. Just one more thing. And you're going to go, Mayday, this is absolutely trivial. d phi over dt at t equals 0 is still equal to omega, right? Earlier I claimed that my angular velocity is just a constant, so of course, at the very beginning of this trajectory, yeah, it's still just omega. My thing starts out moving at omega, and it continues moving with angular velocity omega at all times. But it's really, really important that we see just directly from the math of these features that if I have an acceleration of this form scaled by omega squared, right, and pointing in the direction opposite to wherever my position of this particle is, and if I have a linear velocity that's always perpendicular to my radial position, right? That if I take these facts and and I also know that my angular velocity is constant, right? The combination of these facts tells you immediately together that my particle must be moving on a circle. because now we're going to go the other way around, right? I'm not going to start by claiming that my particle's moving on this circle. I'm going to start with this equation over, or with this form on the left here, perform the exact same manipulations, and we're going to see that mathematically we find the same thing, and that our particle must also be moving on a circle if we choose to represent its position with this equation r e to the I phi. That's my objective here, okay? So let's go ahead and do exactly that. I'm going to go ahead and describe my complex plane again. So this is x equals re of z, and this is y equals imaginary of z. Okay, cool. And now, I haven't connected the fact yet. I haven't connected any facts yet. We're just, all that I'm going to say is I'm going to say my particle, right, is at some position z, and I'm choosing to write it in this form re to the I phi, right? And we don't really have any idea of what this outputs, right? So let me write this over here. So z equals re to the I phi. We know that this on the right here is going to encode some kind of position of my particle, right? Because if I plug in a value for phi and I plug in a value for r, maybe r equals 5 and phi equals, I don't know, pi over 2. We don't really know exactly what this is going to do, but it's going to spit out some number, right? And in the complex plane, a single number is enough to represent a position, right? I don't know if this number is going to have a real part and an imaginary part, just a real part, but this is some number. And as long as we have a number, we can represent a position in the complex plane, okay? Do we feel great about that? Now from here, I need to go and I need to confirm that this position actually corresponds to a position on a circle. And the other thing we're going to do is I'm going to take this variable phi, which again, for right now, it's just a dummy variable, right? We already know the answer, which is great. We already know that we're going to end up proving that this phi here is in fact the same thing as these angles phi here, right? Which makes it easier, right? Because we kind of know where we're trying to get to, right? But I'm just going to assume that this dummy variable phi here, I've chosen to write out phi in terms of some time t, right? So this phi here, I'm just going to let it vary with time, and it's going to happen to vary in this way, where I take some constant and multiply it by t, okay? So I take this constant omega, multiply it by t, and that defines how this random variable phi is going to vary with time. So from here, let's go ahead and calculate out. We're going to find the velocity of my particle, and we're going to find the acceleration of my particle. Sound good? Right, and so of course we have that, that my position as a function of time, z as a function of t, is equal to re to the I omega t. Great. Okay, let's go ahead and go through the statements like we did before. So 1, let's go ahead and get the velocity of my particle. dz dt is equal to r times I omega e to the I omega t. All I did, I just carried out the chain rule, right? I took the derivative. Let's go ahead and match our terms here. So right, here's r, here's e to the I omega t. So this is equal to I times omega times z, right? Do you feel, and right, and z is a function of time. Are we feeling really good about that? I just performed a substitution. Okay, and now let's go ahead and get our acceleration. squared z over dt squared. And this is going to be equal to r times I omega times an I omega again, right? So this is r times I squared omega squared times e to the I omega t. Just really dumb question. What is I squared? We know that I squared is minus 1 because that is how we define I. So this is minus I omega squared e to the I omega t. And of course we can go and we can rewrite this out as, again, just make sure that our substitution, we're feeling good about this, that r times e to the I omega t is z. So this is minus omega squared z as a function of time. Okay, so next, let's go ahead and take this general set of relations, and now we're going to set t equal to 0. I want to observe these relations at a very specific point in time, at t equals 0. So z at t equals 0, this is just going to be equal to, can we plug in 0 for t? Great, yeah, nice and easy. Okay, cool, this is going to be r. E to the 0 is 1, 1 times r is r. Cool. dz dt evaluated at t equals 0. What's this going to be? Oh, well, if z at t equals 0 is just r, then this is simply going to be equal to I times omega times r. Great. And next, if we have dc squared over dt squared, or totally messed that up. What am I doing? Okay, d squared z dt squared, right? The acceleration of my particle at t equals 0 is equal to minus omega squared. And again, we just plug in our position at t equals 0 right in there. This is minus omega squared times r. And let me just take this set of conditions and we're going to move them over to our pretty little picture here. Move these over here to my picture. And let's go ahead and clear the board. Let's clear the board now. And now we're going to go ahead and we're going to start with our little recipe here. So, z at t equals 0. The initial position of my particle is at r. And r, of course, is purely on the x direction, right? Because it's just a real number. So we're at some location, r. Right? And again, I'm using black to represent my particle here, right? Just like I did up here, to represent that this is the initial position of my particle, right? Whereas this, the light blue, was an arbitrary position at some arbitrary time in my loop. So now I'm at some now I'm at some initial time t equals 0, and so I'm at some initial position r. And what's my velocity? Oh, look at this. My velocity is purely imaginary, right? So here was my position. And let me make my colors match. So here is 1, and then really we used red for my velocity, and we used dark green for my acceleration. So here we go. So my velocity is perpendicular to my initial position, right? Because it's purely acting, it's purely imaginary, so it's purely upward, right? And it has a size of omega times r. And my acceleration is purely pointing inward. My acceleration is purely pointing inward. right? And it is going to have some size minus omega squared times r. Well, gee whiz, this sure looks very similar, right, to back up here with the circular motion example, right? And if we really, really want to be careful, right, we can go and we can plug in t equals 0 for each of these terms. If I plug in t equals 0 here, I'm going to output z at t equals 0 is equal to r. If I input t equal to 0 into this guy, dz dt evaluated at t equals 0, right? Do this really quickly. Do it in your head even, right? Okay, we can see that this is just going to be equal to I times r omega. And if I plug in t equal to 0 in this third statement here, d squared z dt squared evaluated at t equals to 0, this is also just going to be equal to minus r omega squared. Again, plugging in t equals 0, outputs 1, this spits out 0, and we're left with minus r omega squared, right? In other words, if we claim that we can write out the position of my particle in this form, re I omega t, and in the form r cosine omega t plus I sine omega t, it turns out, very coincidentally, and I'm saying this kind of sarcastically because it's not just coincidentally, right? We're proving a very important fact here that the initial position, the initial velocity, and my initial acceleration at t equals 0 all point in the exact same direction, right? It's almost as though this particle here, which has a velocity at t equals 0 that's tangent to a circle, right? And it's going and it's looping around this circle. Okay, so hopefully we're really starting to strongly, we're not 100% there yet, but we're strongly feeling that this scenario could be a particle looping around in a circle with some angular velocity omega. How do we show that this is in fact completely true? Well, of course, instead of just looking at the initial positions, we have to think about some of these terms, outside of the initial conditions. And we can really conveniently really just ignore the exact position and the exact velocity functions as a function of time. Although I do encourage to go explore them. And in fact, you can find very generally, specifically by exploring the velocity, that this multiplication of I basically takes your position and results in a 90-degree rotation of the position. I very highly encourage explore that fact. It's, it's a very powerful thing. But all that we really need to look at here is just the acceleration, right? Because the acceleration is what really encodes the dynamics of the problem. So my acceleration, d squared z dt squared, at all times is minus omega squared times z, okay? So what do I mean by this fact encodes all of the dynamics? If I give you the initial conditions that my particle is at this location r, and it moves with some tangent velocity omega times r, as soon as I tell you what this acceleration is, that it pulls the particle inwards in the direction opposite to z, we can basically take little time steps. But basically, if I know that my acceleration is constantly pulling inward with this relation that directly matches the relation of my acceleration for circular motion that we know is circular motion, right? And so at this point, now I am going to officially draw a little circle in here to assist me in my drawing, because now we're really getting to the main point here. Is I go and I move a little bit up, but of course my acceleration is going to pull me inward. And here we go. I took some little time step. Here's my new position here. Let me mark the arbitrary position with the same color I did above, right? But now this acceleration goes and it updates. It updates the position and it updates the velocity, right? And then a little bit more time goes by. Now the acceleration, which this is encoding, is now pulling this particle inward, but now in this direction, right? Still inward. So now it's going to take this and it's going to go and it's going to bend. It's going to bend my velocity a little bit more, right? And it's going to pull me in, right? And basically we can just keep doing that for an infinite number of time steps. And because this acceleration is always acting perpendicularly to my velocity, it never changes. It's never able to change the magnitude of my velocity either, right? So each of these still have a magnitude of omega times r because the acceleration is always acting perpendicularly to them, right? So now I hope we're starting to get even more convinced that this particle is traveling along a circle. Please keep kind of stumbling across more and more facts. Prove to yourself that this multiplication of I in this velocity function here results in a 90-degree rotation, right? So if I'm at some position in the circle here, right, and here's my position z, that I can also, just looking at the position of my particle, immediately deduce that my velocity is going to point perpendicularly to the to that position, right? Because of this multiplicative factor I. And so let me just put all of this together in one very, very clear statement, right? Instead of me just spitballing like things that really feel like, you know, like this is a circular motion. Let's put this all together. So here are my initial conditions. So I have my initial velocity. So my initial position slash initial velocity. These are my initial conditions. And then the blue here, this explains the dynamics of the problem. Okay, and now here's my point. I'm going to call this above scenario A, and I'm going to call this below scenario B. Okay? So A, we know, creates circular motion with constant angular velocity omega. Okay. We're going to take all of these things and we're going to put them all together. Okay? Are you ready for this statement? Because A and B have identical initial conditions, and identical dynamics they describe the same motion. Thus, B is also a particle, right? Situation B is also a particle moving with circular motion at constant angular velocity omega. Oh, right, and of course this is going to be and at a radius of r. Right, and just to make this identical, this statement A I should have also included, and this was at a radius r. So let me go ahead and kind of summarize here that, because A and B, these two proposed scenarios, have the exact same dynamics, and they also start out the exact same way with the exact same initial, the particles start with the same velocity in the same position, that all of this information, if we put it together, allows us to confirm that each of these particles are doing the exact same thing. They're just moving around in a circle of radius r with a constant angular velocity omega. Right? And that's it. One way you can rigorously prove this, what I'm saying about this stuff in the initial conditions, is to actually study differential equations. So this is a fact of, I never explicitly said that this guy here is a differential equation, but that's exactly what it is, right? So this is a fact of linear. I don't just want to spitball, terms that we might know, but this is a fact of linear differential equations. But I hope that, I hope that I don't need to do too much convincing, right? So first off, yes, you can confirm that this statement here, because of how differential equations work, this is a true and rigorously defined statement. But hopefully it feels 100% rigorously defined just by me explaining it, and it clicks in your head that, of course, if my initial conditions are the exact same between two problems, and I have identical dynamics that tell me how my position and how my velocity are changing throughout the problem, the motions are going to be identical, right? I really hope that's 100% convincing. But if not, you can also study differential equations and uh, come across the exact same fact. So yeah, so now let's go ahead and use this, right? And remember, the way that we described our position of this particle exactly was with this expression here. So if we have z is equal to r times e to the I omega t, and of course now we know that this is an exact equal expression to the position of my particle as a function of time with the polar coordinates representation, because we confirmed that the dynamics were absolutely equal between the two. So this is equal to r times cosine omega t plus I times sine omega t. And now we go ahead and we plug in. We just go back the other way. Omega t. This input here is really telling me the angle at any position at any time t. Then we have z equals re to the I phi as a function of time equals r times cosine phi t plus I sine. My angle is a function of time. And then, of course, right, we don't actually need to give an angle some dependence on time. This was a tool that we used to show the same thing. So for any angle, and for any radius r, we have re to the I phi equals r times cosine phi plus I sine phi. Hopefully this video, made you feel very strongly, and there are many, again, you can use the Taylor series and just expand out e to the I phi and, expand out cosine phi plus I sine phi and see that those result in the exact same Taylor expansions. That absolutely immediately rigorously proves Euler's identity, right? However, I wanted to make this video more so as a, yes, I understand that I can perform a Taylor expansion and see that these things are equal, but I don't really see how e to the I phi is connecting in any way, shape, or form to circles, right? And I really wanted to kind of hammer in that intuition and, you know, and ultimately conclusively show, because of the identical dynamics and the identical initial conditions, that, you know, this is, very much rigorously also a valid way of getting to the same fact. So here we go. Here's Euler's identity. So hopefully that was fun for you. It was fun for me. So thank you so much for watching.